Welcome back to this morning session. So today we're going to first listen to Gian Maria Dall'Ara, who will give a talk on video-rich furnace index, D'Angelo class, and the Levico. Please.
Okay, thank you very much. It's a pleasure to be here. Thanks for the opportunity to give this talk. Okay, I'm going to talk about a recent, even if it's 98, as by the last year and a half, collaboration with Samuele Mongoli. From Politecnico di Milano, and hopefully this will be soon on archive in a few days. Okay, and the goal of this talk is to present this work that started as an elaboration of a couple of recent papers. One from Gian Liu from 2019, actually two papers in advances, and recently Adachi and you published a paper in 2020, and both of these works are related to new approaches to a classical invariant in several complex variables, which is the video furnace index. Okay, so, but the way I'm going to present our result is to start from a bit far. In fact, in the first half of my talk, but by the way, how long should I talk exactly? 45 minutes. Okay, thank you. And okay, so in the first part of my talk, I'm just going to present a differential geometric construction, admittedly a very simple one, you will see, but probably of some independent interest, and show how this construction plays some role in several complex variables. And by the way, the construction itself is inspired by a lot of previous work, so definitely it doesn't come out of nowhere. But let me present this construction first. And this is the construction of what we call the core of a distribution. Okay, so during this talk now I'm going to use just the word distribution to be subspace distribution. I'll be a bit clearer in a moment. So there will be no generalized function in this talk, no distributions in probably slightly more common sense. But anyway, so distribution for me today is the following. So first of all, we have n, a real smooth manifold. Okay, and then the distribution V is just the assignment for each point of the manifold of a linear subspace of the tangent space at that point. Okay, so of course this is a classical concept. Let me stress that here we are not assuming much regularity on this object. So you can either think of this as a mapping, if you want, from that attach to each point of the manifold a linear subspace of the tangent space at that point. So this is a real linear subspace. Or if you want, as the corresponding subset of the total tangent bundle. Okay, I'm gonna use the two things interchangeably. And okay, and the only, well, in general, the only assumption I'm gonna make on V is that it is closed. So here closed means in the topological sense. Is closure as a subset of the real tangent bundle of the manifold. Okay, so of course this, as I said, you can think of this as the union of all these fibers, and they are a subset of the tangent bundle. I'm just asking for the moment that it's closed, so a very weak regularity. Particularly the rank, of course, is not constant, and the fiber may change rank from point to point. And there is a very simple object, which is the support of the distribution, and the support of the distribution is just a set of points where the fibers is positive dimensional. It's not the trivial subspace. Okay, so this is just a set of points P on the manifold for which the fiber P is not the trivial subspace. Okay, and this is the support. Okay, And what? Let me give an example of a distribution. Of course, well, you can just to have a picture probably for later reference. Okay, it's clear what I mean, but you have your manifold then, and then you got your distribution. So each point is actually in a subspace. So, for example, you could have the support would be, for example, this curve, which means that outside here the fiber is just the zero space, and here say well, the surface, say that the fiber is one dimensional, for example, and I can depict it just by representing this line, okay, and something like this would happen depending on the point, of course. So just to have an example on the curve, and here, this is, let's say that this is the support. Okay.
Are you making an assumption on the dependence on E?
Well, what you said, the only regularity assumption is you want is closure.
Just
Yeah, so for example, here you should have seen something like closure of the distribution implies easily closure of the support. Actually implies that the dimension of the fiber is semi-continuous in one direction. Anyway, no, I mean it implies that the set of points where the rank is larger than quantity is a closed subset. So that's what we have. Okay, this generality. And then let me give you another construction. So somehow the support is a construction that associates to a distribution a closed subset of the manifold. So you start with a distribution, you got a subset, and we got an operation in the other direction attaching to every closed subset of the manifold a distribution. And this is the tangent distribution. Okay. So, but then, of course, if you start with a generic closed subset, I have to tell you what kind of tangent I'm using, and I'm using a quite relatively naive, simple one, which is sort of the Zariski tangent, but it is a smooth category. So this is sort of an example. So given S, a subset of M, which we can assume closed, everything is closed in the topological sense again. Then we have a distribution. We have the what we could call it the smooth Zariski tangent distribution, which I'm gonna denote just by T of S. Okay, so I have to tell you what is the fiber at the point, and this is the set of say XP, the tangent vectors to the manifold at that point, with the property that XP kills every function in the ideal function vanishing of the set. So for every f which is smooth on the manifold, such that f restricted to S is identically zero. Okay, so this is the Zariski definition of tangent if you want in this smooth category. Anyway, this is this notion of tangent. And it's very easy to check that if you start with any set S, the Zariski tangent is always a closed distribution. Actually, of course, you cannot distinguish a set from its closure, right? Because if a smooth function vanishes on a set, it vanishes on its closure. So really, this is really talking about closed subsets. So we have a construction, the support, attaching to each distribution the support, a closed subset of each closed distribution on a manifold, a closed subset. And we have another construction in the other direction, attaching to every closed subset of the manifold, a closed distribution. It's quite easy to check that this is closed to the set. Okay, and so starting with these two elementary ingredients, I'm going to give the maybe main definition of the talk, which is the notion of derived distribution. Okay, what is the derived distribution? And it does this. Let me put it here. So given D, closed distribution on a rational manifold, its derived distribution is D prime is just the intersection of the distribution with the tangent distribution to its support. What does it mean? I'm just using the two operations that I have in some way. So that distribution, you compute its support. So for example, in this case, what is the support of this distribution? As I said, outside of this piece of segment, the fiber is trivial, so the support is this. Well, this happens to be smooth in my picture, so the tangent, of course, coincides with the usual notion of tangent. And so when you intersect the original distribution with the tangent with support, you keep most of the distribution. So if you can see this picture, here I just put the point where the distribution happens to be tangent with support. So basically, this is D, where D prime in this picture, what is it? It is just a distribution which is 5 or 0 everywhere, except at this point here, where you have this. And this is another distribution, 5 or 0 everywhere, and a certain real one-dimensional line at the point. Okay? What is the meaning of this construction? Somehow we got a distribution on a manifold and a distribution at a certain support. But for some problems, you may want to think of the distribution to be really to look at what is the smallest thing where the distribution is actually supported, right? Because, for example, in this operation, somehow you want just to say the part of the distribution which is really tangent to the set where the distribution lives. Okay? That is, for the moment, it's an abstract construction, but the sense is that you are trying to make the distribution perfect. What does it mean perfect? Let me give you the second definition. So this is perfect. If D is equal to D prime. What does it mean that the distribution is equal to its derived distribution? Just means that, of course, this is always a subset of D, and this is always a D prime subset of D. So to be perfect, it means that they are stable under this operation. In other words, that the distribution is really tangent to its support. So it lives on a smaller object inside the manifold. You can throw away all the points where the fiber is 0, and you really find a distribution in this subset. This is not the case here, and in fact, you have to kill a lot of points. And what happens here is, in fact, that when you cannot expect that when you do the derived distribution, you get something perfect, you may need to iterate the operation. But here you got another distribution. What is its support? Well, it's trivial, the support is just points. What is the tangent to a point? Of course, it is the trivial distribution. And when you intersect the trivial distribution, you derive again, and in this case, you got the 0 distribution. Okay, so if you do this segment here, and here you got the 0. The distribution with 5 or 0 at every point, which I'm going to call the trivial distribution. Okay? Okay, all of this is, of course, a very abstract construction. Sure, because exactly. That's why I introduced the tangent to a general closed subset. Because, as I said, if is just a closed distribution, support is just a closed subset, and then the tangent has to be taken in some weak sense, and this is the sense that we are taking. It's a pretty naive notion of tangent in a sense, because you got a closed subset, and you're really there. For example, the rank of this tangent is k if and only if your closed set is locally contained in a three-dimensional smooth ordinary submanifold. Okay, but this is a convenient way to think about it. And
Gian Maria,
please.
does this definition coincide with the usual one that is in algebraic geometry using strings? When you take the sheet of three defined vanishing over those square, then you have a natural map on the tangent bundle, then you get the
I think so.
then
I think so, but you have to use the ring of germs of smooth functions.
yes.
Because you have this visibility, but smooth function, you can write them as
and then there are the industrial tensor with the appropriate with this strings that you do, right?
yeah, I think so. Yeah. At least yeah.
Is a TPS distribution always perfect?
No, the TPS. Well, TPS is not. That's the question. No, because okay, you can ask what is the support of the tangent, which is something that I wanted to say right now. That the tangent to the support is exactly a set of accumulation points. It's not so easy to understand because you've got a set of points. If the point is isolated, of course you can cook up a smooth function that vanishes there with non-zero derivative in any possible direction. So the tangent to a point is trivial. But as soon as you are not isolated, you got some accumulation and well, or vice versa. If at a point the fiber is trivial, then it necessarily means that you can find local coordinates. That's if you think of what this definition means. You have enough directions to just isolate the point. So the only points where the fiber of the tangent is trivial is the isolated points. So the tangent to a closed subset is perfect if and only if the set S coincides with its set of accumulation points, which means it's perfect in set theoretic terminology. And that's what I wanted to clarify now. And of course, all the terminology comes from there, because the basic example is when n is one dimensional, you want the real one. So what is a distribution in one dimension? I just have to assign to each point a subset of the tangent, which is either trivial or one dimensional. So the support of a one-dimensional distribution contains all the information on the distribution. So there is a bijection between the operation of taking the support is a bijection in one dimension. And so if you translate this operation, what you're doing here, you are taking a distribution, you're taking a support, which is the distribution itself, and then you compute the tangent. And as I said, the tangent is just takes the set of accumulation points. Okay, here is one dimensional. So as I said, the distribution is just the assignment of the number of points plus subset. Okay, and the support is this, and I don't have to pick any vector, of course. And if you look at the tangent of the support, well, here the tangent is 0 because points are isolated, here is one dimension. So when you intersect the distribution with the tangent, it's like just looking at the set of accumulation points. So in one dimension, if you want closed distributions are in bijection, the operation of support with closed subsets of the manifold are in this case, it is a bijection. And the operation here of passing to the right distribution corresponds in terms of the support S of passing to what is sometimes called S prime or the set of accumulation points. Okay. And in fact, here perfect means that your closed set consists only of accumulation points, which is the classical definition. And this shows something that, okay, I showed an example here where you iteration a couple of times the operation before you stabilize. Of course, when you get to 0, then it's stable. But this should clarify, if you remember from set theory, that you cannot expect that this operation stabilizes in a finite number of steps. And okay, in quite rough terms, this is basically how Cantor invented the part of set theory, the theory of ordinals, right? Because he was studying this operation in relation to some problem for analysis of the operation of taking a set of accumulation points. And you realize that it's not true what he probably thought at the beginning, which is very natural. That a number of steps you're going to clean all your set of points like that, and you're going to stabilize, but you need the theory of ordinals. And so, well, at this point we have a complete, a little generalization. Actually, it's a large generalization in terms of what we're talking about, but the proof is exactly the same of this set theoretic theory. And what I mean is that if you recall Cantor-Bendixson theorem, it's a theory which is exactly the theorem stating that the operation is going to stabilize, probably not after finitely many steps, but after countably, well, after a transfinite induction with a number of steps corresponding to a countable ordinal. So let me record you the statement for accumulation sets. Okay, so let's say record Cantor-Bendixson theorem. The Cantor-Bendixson theorem says that given S in R closed, okay, setting well defining S alpha for any ordinal alpha by transfinite induction. So when alpha is 1, this is just the, well, let me write it, by transfinite induction as follows, okay? S0, alpha is an ordinal, so for the 0 ordinal it's just S, and S alpha plus 1 is just with S alpha. When you do the derived set, S is a closed set, then I'm using this notation from topology set theory. And of course, not every ordinal is a successor ordinal, and there is a simple definition for limit ordinals, but okay. And by transfinite induction, you can define this for any ordinal, okay? For any ordinal alpha. And what does the Cantor-Bendix theorem says is that given any closed set, there exists a countable ordinal, so not a finite one, but a countable ordinal alpha 0 such that S alpha 0 is perfect. Okay, so probably no matter how many times you iterate this operation, every time the set of accumulation points in your closed set is strictly smaller than the closed set, the previous closed set. It is getting smaller and smaller, but if you go on by transferring induction, you cannot go on forever. And you have to stop at a certain countable ordinal. So probably infinite, but a countable ordinal. And the point is that, okay, we have the same theorem for this construction of distribution. And the proof is the same. So here there is nothing particularly big. And once you have the definition, you can. And so we have the same theorem. So what the theorem says is that given a distribution, a closed distribution V, so closed set becomes a closed distribution V, well, you define the alpha by transferring induction. And okay, there is, as I said, I don't want to, that there is some technicality because when you work with ordinals, there are limit ordinals, but in this case, it's very simple, just take the intersection along the sequence, it's not particularly. And then there exists a countable ordinal such that this is perfect. Okay, so now what we know is that if I start with an arbitrary closed distribution on a manifold, I can iterate this operation where we are each time trying really hard to have a distribution which is tangent to its support. You may fail finitely and even infinitely many times, but at a certain point you're going to be stable. And when you are stable, what you get, we're going to call the core of the distribution. Okay. Okay. By the way, this is in the application that then we have in mind. We don't use in any particularly different way this fact that if you work with arbitrary distribution, you may need infinitely many steps. This is very interesting if you do it finitely many times. So, but this is what you have in this generality. Okay.
Gian Maria, excuse me.
Sure.
If you do have, let's say, one-dimensional position, singular position, in that case, what's going to be?
You take the tangent distribution to the foliation.
Yes. So it's.
I think the point is that at singularities, the Zariski tangent is going to be larger. So if you're satisfied that the union of two intersecting lines at the origin, the Zariski tangent is two-dimensional. So you have to see what happens nearby, and but typically single isolated points will generate an isolated point in the support, and well.
So in that case, it's going to be perfect according to your definition. Or?
I would say. I'm not sure how you're going to define the tangent. If you define the tangent distribution to.
Well, that, as you said, if you have dimension 2 as one.
I think it's going to be perfect unless you. Should be perfect.
Unless it's singular.
Well, it depends.
Singular.
No, I think that the problem is that you're going to remove a point if the tangent to the support is smaller. But if your singularity is not isolated, I mean, it's not. I'm thinking of a, no matter if it's complex or real, right? If you're thinking of a foliation with singular, it depends if the singularity, if a leaf can be a point or not, according to the definition that you're taking, right? So that's the point, probably.
Yeah. Let me ask you like related question to what you said. So because your manifold like real complex then make.
Now this is real, of course,
yeah.
from the beginning. I'm just talking about real manifolds, and then you can apply this if you want to. But I will comment in a moment on that. So just let me give you the definition. So core of a distribution is just the alpha. Okay, for alpha large. Okay, okay, which means for an ordinal large enough, this is gonna be stable. Okay, so if you want, there is the smallest ordinal, right? An ordinal principle for which this stabilizes. So the core is this object. Okay, what I'm gonna do with that, well, first of all, a rapid comment is really quite simple. I'm not interested so much in applying this to a manifold using further, say, complex structure, but I may want to apply this to complex distributions. But by complex distribution here, I mean that instead of having E, say, inside the tangent of the manifold, you may have inside the complexified. The manifold is still real, but then you look at the complexified tangent bundle, and B, the fiber at every point is going to be a complex subspace. Okay, so these are going to call a complex distribution. And then if the distribution is complex, it's very easy to define the R set because we just complexify the tangent. I mean, the support is just a closed subset of a manifold. The tangent is a real sub-distribution of the real tangent bundle, but then you can complexify just simple way, just canceling. Okay. This is so. The point is that there is a notion of the right distribution also for complex distribution. Okay, even complex. This is clear, right? So when I say complex distribution, I mean nothing related to the underlying structure of the manifold. The manifold is still real, and even complex distribution, the right distribution is just this.
And so, yes, if you were to take the complex plane, then the complexified thing would be a C2. Yeah.
Exactly, absolutely, yeah. Thank you. Yeah, that's a good point. And when I address okay. So, but then one should think what this means, which means that both the real and the imaginary part of the elements here should be tangent, which is a rather stringent condition. Okay? And okay, so now I can move to the main definition. Well, was probably the main definition, but the Levy core appearing in the title. So now we know what is the core distribution, and it's quite simple to define. Well, this audience define what is the Levy core. And so in a word, the Levy core of now I have omega, which is a domain, and this is going to be a smooth, well, typically bounded, even though boundedness is not needed for smooth bounded pseudo-complex domain, okay, in Cn, and of course you got its boundary, and its boundary carries a very important distribution, which is the Levy distribution. Okay, so the Levy distribution is just the null distribution of the Levy form. Okay, so of course you got the P10 of M, which is just what it is, right? It's the P10 of the ambient space intersected the complexified tangent to the boundary. Okay, and the Levy distribution, at least what I'm going to call the Levy distribution here, is just the null distribution of the Levy form. Okay, so let me write them then. So if you want, this is the set of P, ZP, which are the P10 of the boundary, which of course is then a sub-bundle of the complexified tangent bundle, okay, for each point of the boundary, got the 10 vector, which is tangent, and I'm going to require that for any fixed defining function you want this to be 0. This is defined. Of course, it's pseudo-convex, so I can just ask the vector to be 0 when you test it against itself, right? If you don't have pseudo-convexity, you need to. The vector is in the kernel of the quadratic form if it tests 0 against any other vector, but here it's pseudo-convex. So this is a sub-distribution, and it's not so difficult to imagine that it's closed for as long as this is, as soon as this is C2 regularity, then you got enough continuity of the Levy form to ensure that the null distribution is okay. So this thing here, for example, to make things clear, of course, the Levy distribution, for example, is trivial if and only if the domain is strictly pseudo-convex, right? Because at each point there is no kernel. And this is a closed distribution. And then, of course, what is the Levy core is the core of the Levy distribution. and this is the core. Of course, the Levy distribution in this case is a complex distribution in that sense, right? But each point is a subspace of the complexified tangent bundle, and I can consider, for example, what is its support? The support is just a set of weakly pseudo-convex points, right? At the point there is no fiber, the fiber is trivial of the null distribution, if and only if at that point the Levy form is positively definite, which is pseudo-convexity, and then you got a typically smaller subset where you have weakly pseudo-convex points, and then I'm computing this core. And Levy distribution, let me just write this. Okay. So what does it mean? At each step, the operation that you do is you throw away the vectors that are not tangent to the support. So somehow, let me give you a few examples that should clarify a few properties of the Levy core. Okay. So please stop me with your question. I already said that if the domain is strictly pseudo-convex, then so examples. So let's first of all, for examples, remarks. So first of all, it was better to have names. Let's call the Levy distribution N for null, and this C for core, and so N is 0 is trivial, if and only if the domain is strongly strictly pseudo-convex. Right? So of course the core of the distribution is a sub-distribution. So the condition of having trivial core is much weaker than having the mean strongly pseudo-convex. So in a sense, core trivial is some very weak form of non-degeneracy. Okay, so we want to get this inclusion, and to confirm this, if omega is finite type in the sense of tangent, we had this yesterday talking about this definition, then the Levy core is trivial. In particular, having bounded order of contact with complex analytic curves at each point of the boundary allows for a lot of weakly pseudo-convex points, but if you iterate a number of times, this derived operation is going to end up with a trivial form. And this part, in a sense, is a reformulation of the real result of Kettling, but it's a point of view of that result. And so, in this large class of domains which are non-degenerate in this weak sense, every finite type domain is included. And another example which is not finite type, there are examples of domains which are not finite type and still have trivial Levy core. And this is so yesterday first
Maria, is that a general fact if you have a distribution, let's say smooth, so that when you take the V bracket, then after a while you span out the tangent. This means that the core is empty in general.
That's a good question. I should think about this. I'm not sure because this definition of course finite type is not bracket finite type.
Yeah, but I think if you interpret in cone finite type,
yes, at least it depends. To be honest, I didn't think about the relation with Levy brackets. But as I said, there are examples not of finite type, such that the core is trivial. For example, the large class is given by any domain whose set of weakly pseudo-convex points in the boundary is a totally real submanifold. So this includes the examples where yesterday's talk we had just finitely many infinite type points. If those are even if they are isolated infinite type points, then of course be a finite set totally real. So if the set of weekly kilocombs points, which in this language of course means the support of n, so the set of points where you have a vector, non-trivial vector in the kernel of the level form, is totally real. You can interpret this in the sense that it consists of a manifold which is totally real. So of course this does not imply finite type in any possible sense. You can have even an isolated point as you were saying yesterday. It's infinite type. And still this implies triviality core. So what is in the core after all? And definitely if there are complex analytic objects in the boundaries, usually exactly what's kind of abstraction. So if let's say X inside M, so the boundary is a complex of the ambient space, then the T10 distribution to X is contained in the core. This is because at the point of a complex object in your boundary, every tangent, the complex tangent direction at the complex analytic object is in the kernel of the level form. And of course, the complex object itself has this tangent distribution. So when you do the right set here, you're not gonna lose any point. But this is an interesting construction. I don't have time, but there are examples where in your boundaries, you got a complex, for example, in C2, you can have manifolds which are generalized versions of the warm domains, when instead of having a single piece of a Riemann surface like an annulus in the boundary, you got it more complicated. But then you also have other infinite type points. And when you do this core operation, at the first step of the iteration, you kill all the points outside of the complex analytic object, and then you get just that. So somehow the core is able to separate the benign with infinite type points from the really nasty ones, which are typically the ones attached to related to complex analytic objects in the boundary. Okay, now I see I have.
May I ask you a question?
Sure.
Related to the doctor yesterday. So could be possible like a omega that satisfies the visibility and joy visibility property that would be like a trivial core?
I don't know. I was thinking about could be useful. I mean, it's a way somehow to encode any situation where you are really able to tell for some reason that the directions in the kernel of the Levy distribution that are somehow transferred to the support are not really bad direction. This is typically what happens in the deeper Neumann problem and other complex analytic problems. But of course, it depends on the situation. In fact, let me conclude by so my title was, that's why I was trying to put in parentheses the other terms, because I wanted to introduce this object. Let me show you one example of an application which is related to the problem of estimating or studying the Dideric index of the domain, right? So let me take, I don't 14 minutes, not 10 minutes probably. Okay, so let me just show how to so an application of the application, the Dideric index. I'm gonna be sketchy, of course, but soon there will be a paper with a lot of details for anybody that is interested. This is related to what I said at the beginning, other people's work. And what is the Dideric index? We are still in the same setting. Omega is smooth bounded pseudo-convex domain in Cn. And so the Dideric index of omega is the supremum overall positive deltas, say between 0 and 1, with the property that there exists a defining function such that the power delta of this defining function inside the domain is pure supermonic. Okay, so defining function are taken to be negative typically, so I have to take minus r, raise it to the power delta, and change sign to make it positive. And I want this to be plurisuperharmonic on omega for some defining function. Okay. And you can think of the, if the domain is just pseudo-convex, you know that the log with a certain sign of the defining function is plurisuperharmonic. This is a stronger condition, and you wonder for which powers delta, how large the power delta can be taken. The larger the power, the more difficult it is to ensure plurisuperharmonicity. For example, if you got delta equal to 1, you got the nice class of sets which actually have a plurisuperharmonic defining function, which, as we know, is not the case for general pseudo-convex domain. And this is the Diederik-Forness index introduced by Diederik and Forness in 1977, was somehow implicitly in their paper. And they also proved that it's positive, which is, of course, very not trivial, the existence of a positive power with this property. And this is a certain interest in various problems in complex analysis. There are various reasons. At the beginning, there are very interesting papers relating this quantity to the problem of smooth extension of biomorphisms. And from my point of view, it was interesting to investigate. There is an interesting theorem by Kohn from the end of the 90s saying that morally there is some technicality, but if the Diederik-Forness index is 1, okay, this is I'm lying, but if the Diederik-Forness index is 1 plus some assumption, then you can deduce that you have exact regularity in the Neumann problem. So if the datum has some Sobolev order of regularity, the solution has the same regularity. And this implies a lot of nice things in complex analysis. So it was interesting to try to understand if under which assumption we can bound from below the Diederik-Forness index, try to show it's 1, and so on. And here is an interesting theorem. Well, let me put all together in a result, results of a few people. So as I said, you 2019, and there is a joint paper by Adachi and you 2020, and my paper with someone. And the result is this. It's gonna be sketchy, but I hope to convey the idea. Okay. So, okay, the result is formulated in terms of the machinery that we introduced in our paper. I'll try to point out what are the ideas that are really due to these other people. And the statement is something like this: there exists a, well, this is just to convey some idea, a norm-like function, n, and this function takes sub-distributions of n, okay? So you take any sub-distribution inside the Levin distribution and you attach, well, it's norm-like, so in a sense, should be a non-negative number, and such that it satisfies a few properties, which I'm gonna write here. Okay. Okay, so the first assumption is that this there exists means, of course, that we construct it, and it will take some time to discuss how this is done. It's not just an existence, but this is enough to convey the idea. So if you got two D inside E, meaning two sub-distributions of the level of distribution, one inside the other, then this sort of norm is increasing. So the larger the distribution, the larger this norm. This norm is just to convey the idea that it's a quantitative measurement. Okay. The second property is that if you got a trivial distribution, you have 0. And here is the actually new result, which was built in on the previous result by you. And the Diederik-Forness index of omega is equal to 1 over 1 plus n of the Levin distribution, which means that you have some way to extract quantitative measurement of a distribution. And for example, this implies that if a domain is strictly pseudo-convex, the Levin distribution is trivial, this sort of norm is 0, and so this is 1. This is well known. If the domain is strictly pseudo-convex, we have a strictly root for -1 function. And okay, and this is a point from 0 to infinity, and correspondingly this goes from 1 down to 0, and the finiteness of n corresponds to the positivity. This is never 0, and this recovers the original result of the fullness. And I'm going to conclude with my result somewhere. And the idea is that we are able to show that this operation is somehow stable under taking the derived distribution. So really, when we want to compute this quantity for the level distribution is equal to 1 for the core. And so there is a big flip here, because as soon as, even though your domain is not strictly pseudo-convex or not even finite type, but as soon as the level distribution is trivial, this is 0, because, and then the uniformness index is 1. And so in particular, we're able to recover all these consequences for the deep environment problem and so on. So, okay, this was just to give you a flavor of in the paper, there are the details about the constructions and so on. But I think I stop here for your time. Thank you.
So are there more questions to the audience? Mr. Amara?
A couple of questions. First one would be, is that true that if the n of distribution is 0, then the distribution is trivial?
So again, if the n of it is
so if and only if, because the second condition you have one.
you may ask if this is 1 if and only if
No, I think so you have this norm line, right? So n of b equals to 0 if and only is trivial.
no, this cannot be true because of this. See? Because
right.
yes,
Yeah.
so this 0 is implied by having trivial Levi core, but
Yeah.
it's not implied. We also know it's not true. There are examples where Levi core is not trivial and still the n is 0.
Okay, thanks. Second question, like a little bit more naive. So can I see my the distribution, because you presented a very general theory, so as currents?
Well, we didn't try to give
This one.
we didn't try to do that, but I mean,
I don't know, because when you have this distribution,
it's true. Okay, I didn't discuss what's the relation in 1 minute sentence. The way you read this n is well, in particular, the domain could contain a boundary complex analytic object. So in particular, since I'm going to define this for any subdistribution of n, I need to be able to define it for any tangent distribution to a complex submanifold. So the way you present it is generalized to this setting, a construction which should be there ready for complex manifolds. And for complex manifolds, what you do is you attach to, if a complex manifold is contained in the boundary of a pseudo-convex domain, there is an attached homology class in the first Beran homology. And then this n is really a sort of norm, it's almost a norm, just quasi-triangle point and things like that. So it's really quantitative measures of the homology classes, and that's the way you extend. So in a sense, you want to pair differential forms, one forms with, but there is no integration going on.
It's like relate the mass of this. If I can relate this to currents, I can relate the mass of the current.
But there is no integration going on, as I said.
The
it's a
current
pointless estimate, because this ambition is somehow, there is harmonicity is a pointwise condition, it's not a condition on average.
Another question at the moment, why is the DFT interesting? Because I have no idea.
Well, the information index is interesting. Probably I was talking too fast, but I was saying that one example is that the information index 1, there is a theorem by Kohn from 1999 saying that the information index 1 plus some technical assumption implies that you have the best kind of regularity in the development problem. And this in turn implies a lot of things. For example, for the class of domains, if you want as a corollary of this, in the class of domains with trivial Levi core, you've got smooth extension to the boundary of biomorphisms. This is just by attaching this result with a lot of other machinery, Pepperman, Belli, Gotchka, and common results, and so on. So this is an example.
Just wanted to ask, is there an algorithm in order to construct the score in terms of commutators?
Yeah, this is related to what. So first of all, let me say that, as I said at the beginning, of course, this idea of eliminating the transverse direction doesn't come out of nowhere. For example, the way there is a paper in the 70s by Dilligan for Ness proving that if you are real analytic, then you are finite type in the sense of D'Angelo. Basically, there is something like that going on, except that there is no formalization of this procedure. I don't know about an algorithm. So maybe the question could be something that we wanted to think about is, in a sense, the construction is also local, because what you do when the local vanishing of the core depends just on the local properties of the distribution. So you could start with a real analytic, real analytic boundary and try to decide in terms of the.
So the reason I'm asking is John D'Angelo has been asking for 40 years if one can come up with, in the pseudo-complex case, a commutator description of this finite type. So as you know, that the finite type, if you have finite type, then you have 0 core, trivial core.
Yes.
So I was thinking, if there's sort of a commutator description of the core, then it could be that what John is trying to actually construct, not finite type.
Yeah, the problem is that, well, yeah, could be, but the point is that as you move away from finite type, you have to remember the original Cantor Bendixson statement. In all these examples, there are finitely many steps. Right. But if you take a general pseudo-convex domain, just smooth, you cannot expect to have only finitely many steps, because you need some, and you can cook up examples. In the same way, I mean, already in one dimension by the Cantor construct, the way you build sets for which you need countably many steps, infinitely many steps, you just take a set of points, then for each set of points, you build a sequence accumulated to the points, and then for each point of each sequence, you build the accumulation point. So you can cook up a closed set with this ordered structure, and you can easily build the domain into some kind of orthodox domain with a set of weakly pseudo-convex points is like that. So if you allow these nested examples,
no, I'm just thinking about it. I mean, it's really it's a local,
yeah,
it's a local thing. So I don't care. Of course, it would be interesting. I mean, somehow the state form itself is complicated.
Yes, sure.
So somehow an algorithm. There are these, algorithms. Cone algorithms. But I know John was thinking about it for 40 years. How to use algorithms to drive by type. The other thing is there could be that it's not true, but maybe instead you're describing trivial core or something.
Yeah, thank you. Thanks for the question.
So if there are no questions,
Just a short one. I think there are some relation with the squeezing function, right?
It's very for nice index.
Sorry? Yeah, with the Cornex index, and then so maybe with the core or something, or
I don't know about this, but I have nothing intelligent to say. Sorry.
no, okay, well, just
check on the chat. It doesn't seem to be anybody in our distant audience who wanted to ask a question. So let me ask you to send that again.